incoming packet queues. The head pointer indicates where new packets that just arrived will be enqueued, and the tail pointer indicates where the runtime will process packets from. So suppose that one time we run the algorithm, our queue looks like this. Over the next 5 microseconds, some packets might arrive, and the runtime might process some packets. So the next time we run the algorithm, the head and tail pointers have now moved. And we can see just by looking at this diagram that there are 2 packets that remain queued since the last time we ran the algorithm. So this application is in fact suffering from compute congestion. But we can actually perform this check really efficiently by observing that the head pointer from the previous iteration is greater than the tail pointer from the current iteration, and this indicates that compute congestion is occurring. If, in contrast, the runtime had processed 2 more packets so that the head and tail pointers now matched, we would see that congestion was not occurring. And all these head and tail pointers are stored in memory that's either shared with the runtimes or with the NIC or the storage devices. So the I/O kernel could read all these head and tail pointers quite quickly and without synchronization costs. In addition, this approach of using head and tail pointers is quite generalizable, so it's likely to work for other new devices that we might want to incorporate in the future. The 2 key features of this algorithm are that it considers multiple sources of congestion, and that its mechanisms are efficient enough to run every few microseconds. No distribute packets across flows using some sort of flow consistent hashing, for example, using RSS. And then they have each core pull a specified NIC queue. With this approach, we've achieved both of our goals of load balancing and cache affinity, and we don't require very much communication between cores. But things become much more complicated when core allocations are dynamic. So if you were to use the same approach, when you reallocated a core to a different application, you would now steer packets to a queue that's no longer getting pulled. So clearly we need some way to adapt, and we need to be able to adapt extremely quickly within a couple of microseconds. So one approach to deal with this would be to reconfigure the mapping from queues to cores whenever core allocations change. The benefit of this approach is that we don't have to reprogram the steering rules in the network hardware, which can be time-consuming. But the drawback is that cores have to agree on the new mapping every time core allocations change, which requires coordination. Another approach would be for each core to always pull the same hardware NIC queue, and to reconfigure the packet steering rules in the hardware NIC whenever core allocations change, so that we only steer packets to the active queues. The benefit of this approach is that there's less synchronization between cores, but the drawback is that you have to reprogram the NIC steering rules on every core allocation. We've actually implemented both of these 2 approaches in Shenango. The system uses the one on the right by default because of the reduced coordination between cores. This is actually the same approach that an existing system called IX has taken, but in IX, updating flow steering rules takes about 100 microseconds or more, which is about 10 times longer than our flow steering rule updates take. And there are 2 main reasons for this difference. The first is that IX's network stack has no locking in it. So this means that packet processing in the common case can be quite fast, but the drawback is that it makes core reallocations more complicated. In order to migrate a set of flows from one core to another, IX has to stop processing them on the first core, then reprogram the NIC, and then re-enable processing for this set of flows on the new core. And this whole process takes a lot of time. In contrast, because Shenango has per-socket locks, it is safe for packets in the same flow to be processed in parallel on multiple different cores. So packet processing does not need to stop while we reprogram the NIC rules. The second reason for the difference between IX and Shenango is that Shenango uses different mechanisms for reprogramming the NIC, and these mechanisms avoid system calls and complete much more quickly. We have implemented Shenango. The runtime has support for UDP and TCP, and support for block storage reads and writes, and we have bindings for C++ and Rust. We've also implemented the I/O kernel and a kernel module called kschedge, which mediates between runtimes and the I/O kernel in order to reallocate cores. In total, our system is about 19,000 lines of code. Our evaluation of Shenango focuses on 3 main questions. First, how well does Shenango reconcile the trade-off between CPU efficiency and network performance? Second, how does Shenango respond to sudden bursts in load? And third, how do Shenango's individual mechanisms contribute to its overall performance? For our experiments, we have 1 server running a 40 gigabit per second NIC and 6 client machines with 10 gigabit per second NICs. Clients run our own open loop load generator, which is built on top of Shenango. Requests follow Poisson arrivals and use TCP. And we evaluate 4 main systems. First, we evaluate Linux. Linux doesn't use kernel bypass networking, it doesn't have support for lightweight threading, and it readjusts tasks across cores every 4 milliseconds. Next, we evaluate Zygos, a state-of-the-art kernel bypass networking stack. Zygos doesn't have support for lightweight threading or support for reallocating cores across applications. Third, we evaluate Arachne. Arachne is a state-of-the-art user-level threading system, so it has lightweight threading, and it adjusts core allocations across applications every 50 milliseconds. But Arachne does not integrate with a kernel bypass network stack. Finally, we evaluate Shenango, our system, which has support for kernel bypass networking, it supports lightweight threading, and it reallocates cores across applications every 5 microseconds. So let's revisit the memcached experiment that we looked at earlier in this talk. To refresh your memory, we have a client that sends requests to a server. The server looks up the value in memcached and responds. And we also have a batch processing application running on the server. We saw that Linux achieved poor performance for memcached, but got some throughput for the batch application, while Zygos had good performance for memcached, but no throughput for the batch application. So now let's look at how Arachne performs. We can see that Arachne improves over Linux. It maintains lower tail latencies for memcached, and it's also able to reallocate cores across applications, so it achieves some throughput for the batch processing application. For Shenango, we see that we're able to maintain low tail latencies of less than 100 microseconds up to over 6.6 million requests per second for memcached. And at the same time, with Shenango, at lower memcached throughputs, we're able to trade throughput for memcached for throughput for the batch processing application. So what we can see here is that Shenango is able to maintain tail latency similar to a state-of-the-art kernel bypass system, Zygos, while fully utilizing the CPU for productive application-level work, and thereby achieving high CPU efficiency. And there are a couple of interesting things to note about these graphs. First, if we compare the tail latency of Linux and Arachne to that of Shenango and Zygos, which are the kernel bypass approaches, we can see the benefits of using kernel bypass networking. And it's only possible to reallocate cores really quickly while using kernel bypass networking because Shenango can reprogram flow steering rules very quickly. The second thing to notice about this graph is that Shenango achieves much higher throughput for the batch application than any of the other systems we evaluated. And the reason for this is that Shenango reallocates cores across applications so quickly that it doesn't need to provision memcached with extra cores in order to maintain low tail latency. And this frees up extra cores to be used by the batch processing application. So now let's revisit that experiment we looked at earlier in which we suddenly changed the load. So again, we're going to change the load offered to the system every 1 second. And we saw that Arachne achieved poor tail latency every time we increased the load and took hundreds of milliseconds to recover. In contrast, Shenango is able to maintain low tail latency across all of these changes in load, including when we suddenly change the load from 100,000 requests per second to 5 million requests per second. And the reason for this is that Shenango reallocates cores 10,000 times as often as Arachne. So this allows Shenango to react very quickly to changes in load before any queuing builds up in the system. So now we're going to analyze one particular aspect of Shenango's performance, which is its scalability. So we're going to look at how throughput scales with the number of cores in use by an application. So we're going to run a TCP echo server that simply echoes back packets when it receives them, and we're also going to run a batch processing application on the server. On the x-axis here, we're going to plot the number of cores that we give to the echo server, and on the y-axis, we'll plot the maximum throughput that we can achieve with this echo server, while still maintaining tail latency below 100 microseconds. We can see that Shenango scales throughput linearly with the number of cores made available to it. And you might think that this is not particularly remarkable, but it turns out that an earlier version of Shenango, which we call Shenango indirect here, did not have this property. The reason for this is that Shenango indirect, the I/O kernel steered all packets to and from runtimes. So it would receive packets from the network hardware, steer them up to the runtime cores, and on the egress path, it would collect packets from runtimes and then send them out on the NIC. In contrast, Shenango direct, which is what I've described so far today, has runtime cores directly interact with the networking hardware. And this approach allows throughput to scale with the number of runtime cores, rather than being bottlenecked by the I/O kernel. And the reason that we didn't take this approach initially when we designed Shenango indirect was that we didn't know how to reconfigure flow steering rules at microsecond scale. With Shenango indirect, we could reconfigure packet queues in software instead in the I/O kernel, which was easier. So this demonstrates that Shenango's scalability is only possible because we can reconfigure hardware flow steering rules so quickly. So earlier in the talk, I also made this claim that it's very important that we consider these multiple different signals of congestion in our congestion detection algorithm. So here I'm going to evaluate that claim. Again, we're going to run our TCP echo server with a batch processing application. And we're going to try out a couple of different variants of our congestion detection algorithm that try omitting one of these different congestion signals. So either we'll ignore the queuing of threads or we'll ignore the queuing of packets. So this is what performance looks like if we just run our normal congestion detection algorithm. The top graph shows the tail latency we achieve for the echo server as a function of offered load, and the bottom graph shows the throughput we achieve for the batch processing application. Now let's look at what happens if we don't consider the queuing delay of packets. We only look at the queuing delay of threads when deciding if an application needs more cores. There are a couple of things to note about this graph. So first of all, if we look at the very lowest loads here, we can see that the tail latency for this approach is actually lower than for the full algorithm. And this seems sort of counterintuitive, but what's actually going on here is that if we don't consider queued packets as a congestion signal, we have no way of waking a core for this application when packets arrive. So in order for this application to work at all, we have to continuously dedicate one core to busy spinning for it. So this produces lower tail latency at this very low load, but means that we always have to waste a core, even if there's no work for this application to do. And this might not seem like a big deal to waste one core for an application, but if you're running many applications on your server and you have to waste one core for each of them, all of this wasted CPUs adds up. The second thing to note here is that there's this huge tail latency spike at low loads. So when we don't use queued packets as a signal of congestion, the I/O kernel can't react as quickly to bursts in load. And the reason for this is that the way that packets are handled is when they first arrive at a system, they're enqueued into the NIC. And then later, the runtime in Shenango will dequeue them from the NIC, find the corresponding threads to wake up, mark these threads as runnable, and put them in the run queue. So if we only look at queued threads as a signal of congestion, we can't react immediately when queues begin to grow in these in the hardware NIC queues, and we have to wait until the runtime has actually done some processing before we see the queues growing in the run queue and can react to congestion. So with this variant, the I/O kernel reacts much more slowly to changes in load, and this delayed reaction causes our tail latency to increase significantly. So now let's look at a variant where we only consider packets. We don't consider the queuing delay of threads. With this variant, our Echo server performs fine, but we can see that we don't achieve any throughput for the batch application. The reason for this is that our batch application doesn't send or receive any packets. So if we only use packets to decide when to add more cores, we don't add any cores, and it never achieves any throughput. So what we can see from this graph is that if we don't consider all of these different congestion signals that I've talked about, we either have to waste cores busy spinning, we achieve poor tail latency, or we just can't support some classes of applications. So it's really important that our congestion detection algorithm considers all of these different signals of congestion. And for workloads that include storage, it's really important that they consider the queuing of storage requests as well. So to summarize, Shenango reconciles the trade-off between low tail latency and high CPU efficiency at servers by reallocating cores across applications at microsecond granularity. And it does this using an efficient congestion detection algorithm, a component called the I/O kernel, and a dynamic approach to flow steering. Our code for Shenango and for our experiments is available on GitHub. So now I'm going to talk about Chimera. Chimera is ongoing work, and it's a system that we're proposing that builds on top of Shenango. While Shenango focused on the end host behavior, Chimera focuses on the behavior of the network. So far we focused on two main goals, CPU efficiency and low latency. But with Chimera, we're going to add a third goal, which is network efficiency. We're going to look at what happens when, in addition to the CPUs being a contended resource, there's also congestion in the network. So there are existing systems that have looked at achieving high CPU efficiency and low latency, such as Shenango. And there are several existing systems that have looked at achieving low latency with high network efficiency. But to date, no existing system has looked at providing all three of them together. And this is what we target with Chimera. In order to use both the network and the CPU efficiently, we need some coordination between the two. So the question we ask here is, can we co-design congestion control and CPU scheduling to optimize for both low latency and high resource efficiency? This way, congestion control can make decisions that utilize CPUs efficiently, in addition to using the network efficiently. So before we discuss how we might achieve this, let's look at a couple of examples of how this might be beneficial. In our first example, suppose we have two applications running on a server. Application A doesn't have any requests waiting to be handled, and application B has a long queue of waiting requests. Now suppose we have some incoming traffic for the server, a long flow for A and a short flow for B. Which of these flows should the network decide to send first? With a lot of existing congestion control protocols, they would choose to prioritize the short flow. So the flow for B would get sent and end up waiting in this long queue at B. In this case, this may not have been the optimal decision. If the network had sent the flow for A first, A's latency would have been improved, and B's latency may not have been impacted at all. So this example illustrates that if our congestion control protocol had knowledge of which applications could handle work sooner, it might be able to improve end-to-end application latencies. As a second example, suppose we have two applications running on a server, a compute-intensive application such as MapReduce, and a network-intensive application such as a video upload server. Again, suppose we have some incoming traffic for this server, some flows for MapReduce, and then some bulk flows for the video upload server. How should the network decide to allocate bandwidth between these two different competing flows? One approach might be to prioritize the traffic for the compute-intensive application, over the network-intensive application to ensure that we can always keep the CPUs on our server busy. However, this might waste bandwidth on requests that will just sit in queues, or even worse, they might be canceled entirely if they take too long to complete. So instead, we could try to prioritize the traffic for the compute-intensive application, but only up to a specified rate limit. But if we do this, it's unclear how we should set the rate limit. If we set the rate limit to be too high, we return to the situation I described before. And if we set the rate limit to be too low, then we might not be able to keep our CPUs occupied on the server. So what we can see here is that if our congestion control algorithm had knowledge of how busy the CPUs on the server were, it might be able to better ensure that both the network and the CPU were kept fully utilized. So motivated by these two examples, our goal with Chimera is to co-design the network and the CPU. So we want to improve congestion control by incorporating some information about how busy applications are. And this raises a couple of questions. So first of all, what type of congestion control is best suited for this purpose? Second, what are the best metrics for characterizing application busyness? And third, how can we go about measuring application busyness? So first, what type of congestion control should we use? We can broadly categorize approaches to congestion control based on where in the network the decision is made about which flows to prioritize. So for example, with sender-driven approaches, senders encode priority information in each packet, and then end hosts and routers and switches enforce these priorities, so the decisions are made by the senders. With in-network approaches, senders encode some information about their application demands in packets, and then routers and switches along the network paths enforce these or decide how to mediate between these different competing applications. And finally, with receiver-driven approaches, the receivers make the decisions about how to mediate between different incoming flows that are competing for a congested downlink. And of these different options, receiver-driven approaches are best suited to our needs. The reason for this is that if we consider all of the flows that are sharing a congested downlink, it is easiest for the receiver to gain visibility into the busyness of all the destination applications for all these flows. So what metrics should end hosts use to characterize application busyness? The question we want to answer here is if an application were given more work to do, how much progress would it be able to make in the short run? And we want a quantitative metric that allows us to compare across different applications. So one option for such a metric would be to look at CPU utilization. So for example, if the red application here is using all the CPUs that it's allowed to use, and the purple application is only using half of the CPUs it's allowed to use, we might say that the purple application has a higher potential to make progress, because it has available CPUs it could take advantage of if we gave it more requests to handle. However, there are situations in which CPU utilization isn't sufficient. So for example, the purple application may be suffering from lock contention. In this case, if it's bottlenecked on lock contention, it may not actually be able to get more work done if we were to give it more requests. So for this reason, CPU utilization alone is not sufficient. Instead, we might try considering queuing delay. So for example, if this red application has a short queuing delay and the purple application has a long queuing delay, we might choose to prioritize requests for the red application because it will be able to handle them sooner. Queuing delay is beneficial because it implicitly captures bottlenecks on other resources. So for example, if one of these applications was suffering from lock contention, its incoming queue would grow. However, there are situations in which queuing delay alone is still insufficient. So for example, suppose we have two applications that both have no queued packets and they have idle CPUs, perhaps because the network is currently heavily contented. In this case, if given the opportunity to send one packet to this server, we'd prefer to send the packet that enables the most work to be done. So we would prefer to send the packet to the application that has the highest CPU usage per request because it can make the best use of the CPUs. So what we really want here is a metric that incorporates information about both CPU utilization and queuing delay. So one way to combine these two into a quantitative metric would be to use queuing delay as a primary metric, and then to use the CPU usage per request to distinguish between applications that had similar queuing delays. But you could imagine combining these metrics in other ways as well. Since Shenango has visibility into both, so our next question here is how can we go about measuring application busyness? And this is difficult to do in commodity operating systems today because there are many different places in the system where work can queue. So for example, incoming packets can queue in socket buffers, threads can queue in run queues, and applications can also dequeue requests from the socket buffer and then queue requests internally. So it's difficult to determine how much queuing delay a request actually incurs in a commodity operating system. But fortunately, Shenango provides a solution to this problem. Shenango and some other recent systems have visibility into thread and packet queues, as well as into the number of cores used by each application. So they can easily estimate both CPU usage and how much queuing delay an application is incurring. So combining all these ideas, we propose a system that we call Chimera. Chimera is based on Shenango and receiver-driven congestion control. So recall that in Shenango, applications run in runtimes, and the IO kernel monitors them for congestion and decides how many cores to allocate to each. With receiver-driven congestion control, receiving end hosts generate grant packets, which they send back to senders, informing them when it's their turn to send. These grant packets then clock the flow of incoming traffic. So we combine these ideas to create Chimera. We augment each application in Shenango with an additional grant queue and augment the IO kernel with the grant arbiter. The grant arbiter uses the IO kernel's existing data about allocated cores and queue occupancies to determine each application's potential to make progress. Applications generate grant packets just as they normally would with receiver-driven congestion control, and the grant arbiter prioritizes outgoing grant packets based on this potential to make progress. These grant packets then clock the flow of incoming network traffic, and in this way, congestion control can take into account information about both network and CPU utilization. So to summarize, Chimera is a proposal for how to co-design congestion control with CPU scheduling in order to optimize for low latency and high efficiency for both the CPU and the network. This has the potential to enable resources to be operated at much closer to their capacity, thereby reducing over-provisioning while still achieving low tail latency. Chimera raises a couple of interesting questions. So first of all, in this talk, I focused on how we could modify congestion control to take into account what's going on in the CPU. For best resource efficiency, though, it might also be beneficial to modify CPU scheduling to take into account what's going on in the network. Another question is, should potential to make progress consider application-specific information, such as how useful a given request or response might be to the application? And finally, should Chimera consider the utilization of other resources beyond CPU and network, so for example, the utilization of storage devices? So now I'd like to describe a couple of the key things that I've learned from the research I talked about today. So one of these is that for best performance, it's really important to consider the networking and the CPU scheduling together. And this was done very explicitly with Chimera, but this idea also was apparent from Shenango as well. So I demonstrated that it was very important that our congestion detection algorithm used this signal of how much queuing of packets was occurring. And without this signal, it was really hard to achieve as good performance. So demonstrating the importance of integrating these two ideas. Another key thing that I've learned from this research is about the capabilities of NIC hardware today. So for Shenango, we were pleasantly surprised that we were able to extract enough information from our NIC in order to run the congestion detection algorithm, and that we were able to reconfigure flow steering rules so quickly. However, there's still room for improvement in the capabilities that the NICs expose. So for example, our NICs today do not explicitly expose a head pointer, indicating the index of the packet that arrived most recently. So instead, to find this information, the IO kernel starts with a pointer from where the runtime said it last processed a packet, and then it repeatedly probes successive entries in the descriptor queues until it finds an empty one, and this it knows is the head pointer. So this method still works, but it's inefficient. It requires more CPU usage in order to do this probing. So NICs could make this easier if they explicitly expose the index of the most recently arrived packet to the software. And similarly, with the most straightforward method of creating flow steering rules in our NIC, reprogramming them is too slow. So we had to implement our flow steering rules very carefully in order to make sure that we could reprogram them quickly. So while NICs today expose enough features for Shenango to work, there are features in the hardware and of the drivers that could be improved to enable even more efficient systems in the future. Overall, Shenango makes significant progress towards making high CPU efficiency in data centers achievable. And if it was deployed today, it could significantly improve CPU efficiency already. That being said, there are still ample opportunities for further improvement through proposals like Chimera or through examining other components of the end-to-end system, such as the interface between NICs and software. So these are interesting challenges to tackle in the future. So before I wrap up, I want to thank all the people who made this research and the research I've done earlier in my PhD possible. So first, I want to thank my advisors, Hari and Adam. I've worked with Hari the entire time that I've been at MIT. I think the biggest thing I've learned from Hari is the importance of understanding and communicating the key ideas behind a research project. I think Hari is really good at separating what's interesting and what makes something novel from sort of the implementation details. So I've learned a lot about how to distill the key ideas and how to articulate them in papers and in talks. So I've worked with Adam for the last 2 years since he joined MIT, and from Adam I've learned a lot about how to build systems that really work and perform well. One of the things that Adam is really good at is taking some results that don't really seem to make sense and asking the right questions to help you drill down and understand what's really going on. So from Adam, I've learned a lot about how to measure systems, how to understand them, and how to improve them going forwards. Next, I want to thank Franz. Thank you for serving on my thesis committee, but more importantly, for all the things that I've learned from you as a partial member of PDOS over my time at MIT. So from PDOS group meetings, I've learned a lot about how to structure talks, how to analyze research papers, and how to write research papers. Obviously, this is a group effort from all of the professors and students in PDOS, but I think Franz's feedback played a big role in that. Next, I want to thank all of my collaborators from all the different research projects I've worked on, both past and present. In particular, I want to thank Josh, who I worked with really closely on Shenango. And then I want to thank everyone else who I work with and spend time with on G9. You guys make coming into work more fun. And I want to thank Sheila, who takes care of like food and hotels and reimbursements and just makes everything so much easier for all of us. And I want to thank the Hertz Foundation for their support. And then outside of G9, I want to thank all my other friends in EECS, especially this group of 5 women. And I really want to thank the cycling team. I've had a really great time riding and racing with you guys over the last few years. You guys have given me a lot of much appreciated breaks from research. And finally, I want to thank my family and my boyfriend Daniel for all of their support. So in summary, today I talked about how we can achieve low latency and high efficiency in data centers. I talked about Shenango, which is a system that reallocates cores across applications at microsecond granularity. And I talked about Chimera, which is a proposal for how we can co-design congestion control and CPU scheduling. Thank you, and I'm happy to take questions. Yeah, so I think, so there are a couple of things. So yes, we can react every 5 microseconds. In practice, none of the workloads that we've run actually react that often. I think on average, the fastest we've seen is every 20 microseconds, which is still pretty similar. It's not quite every 5 microseconds. So yeah, that's the granularity at which we actually react in practice. And I think, so there are a couple of things. I think previous systems, this wasn't an explicit goal for them. They didn't realize how important it was to react quickly, so they didn't try to make their mechanisms fast enough. But some of them rely on slower mechanisms. So for example, X reallocates cores across applications, but their mechanisms for reprogramming the NIC flow steering rules are too slow. They might have been able to discover the same mechanisms we did if they had really tried to optimize this. And then there's another system, Arachne, that I talked about that reallocates cores every 50 milliseconds. And their mechanisms for reallocation also still are not fast enough. I think they take about 30 microseconds at least, and that's because they use sockets to interact between applications and the component that's reallocating cores. Does that answer your question?
I guess that helps. But what about just basic context switching? What's the cost of, I don't know, flushing the caches and the registers or whatever is how much does that cost?
Well, so when we actually reallocate a core, the core reallocation takes about 5 microseconds to complete. It depends whether you have to preempt an existing task or not. So I think it's like a couple of microseconds if you don't, and it's up to like 7 if you do have to preempt an existing task. So we can't, at least with our current mechanisms, reallocate much faster than 5 microseconds. Yeah?
So with the IO core system, you have a dedicated core that does all the scheduling. But I assume the work it's doing is linear on the number of other cores, and we see in the recent processors that like the next thread records are going to have 128 threads. Do you suspect that you might have to distribute that over multiple cores, and if yes, how do you want to do the communication?
Yeah. So I think like that's a valid concern, but right now the amount of work that the IO kernel is doing is actually pretty small. It spends a lot of time just like spinning, waiting for things to happen. So I think at least for the foreseeable future, we could just have one core dedicated to the IO kernel. Eventually you might need to have multiple IO kernels, but I don't think we need that today. Yeah.
So two questions. So you mentioned that you were able to reprogram the flow steering extremely quickly, faster than the masters usually. Can you describe a little bit what makes that possible? Like, is that something that's kind of like very new to recent NICs, or what has changed? second question about Chimera. So if you have like a system like Shenango that can reallocate cores extremely quickly, it seems like whatever workload I throw at the server, you'll be able to like handle it efficiently because you can always move like cores around.
Mm-hmm.
Does it actually mean that there's less of a reason to coordinate congestion control and CPU scheduling, or am I missing something there?
Yeah, I think that's a good question. I think, like if you imagined running in a virtualized environment where that wasn't possible, you would definitely still have the issues that I talked about today. But I think, yeah, that's a good question. For your first, wait, remind me of your first question.
Just
Oh.
the next
Yeah, so I think there are a couple of issues there. One of them is that like if you just use like sort of the most straightforward approach of reprogramming the RSS redirection table, like this usually involves a system call, which takes a lot of time. So instead we used a bunch of match action tables, which is possible in our Mellanox NICs. And I think we do take advantage of some features that have only recently become available in these NICs.
You mentioned memory cache.
Mhm.
If I switch to a new process that's brand new and the cache is completely cold, in 5 microseconds, I only get to load about 100 to 1,000 cache lines. And now, assuming I got a bunch of jobs that are doing the same thing on some database, the high level knows the database, of course, are already shared and probably in the cache. But if they're all really different, you have to really think about, making sure this person, after he loads his cache up, it doesn't all disappear when you switch to someone else.
Yeah, so one of the things we do in Shenango is that when we allocate a core to an application, we try to reallocate a core that it's used recently in hopes that some of its state is still there. So if you end up sort of reallocating a core back and forth between these two applications really quickly, then the hope is that some of that cache state is still present when you do the switch. There is still a cache penalty to switching cores between applications. But it's only if they're all sharing the L3 cache, then it's only the L1 and the L2 cache, which is a smaller amount of data.